All right, welcome back. In this video here, we're gonna go over different types of hypothesis testing, and then how do we obtain the critical values. These are the boundary, value that determine where our cutoff value will be. So that way, we either reject the null hypothesis or not. And then we're gonna go over how do we obtain the p-value from the sample data as well. So these two things here, these two different methods. So these are the methods. So these are two different approach to reach the conclusion of hypothesis testings. Okay, so let's start with the type of test first, and we'll go into that in a second. So it said depending on the claim being tested, the critical region could be in the two extreme tails. It could be in the left tail, or it could be on the right tail. Okay, so if the null hypothesis, if the null hypothesis contains or has a symbol less than, okay, then the test is left tail. Okay, and what does that mean by the test is left tail? It means that a cutoff value, the critical value that determine where the values are significant low or high, it will be this shaded region. So we're gonna shade this right here. So this here is gonna be a critical region, meaning if our test statistics falls in this region, we reject the null hypothesis. So this is where the critical value would be. Okay. Okay, so this is where the cutoff value, this is what determine, whether we reject the null hypothesis or not. So this would be the non-critical region. Okay, all right. What about right tail test? Okay, what does it mean to have a right tail test? Well, it means that if our no alternative hypothesis include, a greater than inequality, then we have a right tail test. Okay. And a critical region, it will be on the right side of the graph. So this is the critical region. This is the critical value. And the critical values could be a z critical value or a t critical value. We learned that in chapter 7. What about two-tailed test? Well, to have a two-tailed test where we have two possibilities, the critical value can be on the right side of the graph or the left side of the graph here, and both of these are critical region. If the alternative statement, contain the not equal sign, okay, then we have the critical value separate the significant sample test statistics to be over here and over there, two possibilities, and then these are the values. These are critical values. I kind of remind you the range rule of thumb when we look at the boundary values for unusual and usual data value, kind of like that. Okay. Now let's look at an example how to find critical values. Okay, so the critical values, we're gonna make a note that critical value there can be z or t. Proportion hypothesis testing, we're gonna use z critical values, and if it's mean hypothesis testing, then we're gonna use t critical values. So this is saying that determine the critical values for a hypothesis test at 5% significant level. So this is the probability of making type 1 error. This is the probability of rejecting a true null hypothesis. This is saying the area, the probability that we have sample statistics that is exceed the 95% or within the top 5%. And how do we find the z-score that separate those two regions? Okay, so if it's left-tailed test, given alpha is 0.05, if it's left-tailed test, then our critical value will be on the left side of the graph. So if it's left side of the graph, so this is our alpha, 0.05. This is the critical region, okay? This is the cutoff value, okay? So this is going to be our critical value here. So this is going to be Z equals negative 1.645. And how do we get that critical value? To get this one here, we just do inverse norm. Area to the left is 0.05, and that should give us that critical value. Okay, so this is the cutoff value that determine whether a sample test statistics falls in the critical region or not. Okay, if it's right tail test, okay, then the critical value will be on the right side of the L-shaped curve. And then again, this is alpha equal to 0.05, that area, that probability. And this is the critical value. And that critical value there will be Z, a positive value, Z equal to 1.645. Again, you can obtain this using, a normal CDF. Not normal CDF. You can do inverse norm, actually. You can do inverse norm of 0.95. That should give you it. Okay. So now moving on to two-tail tests. So if a test involves two-tail, meaning two critical values that that separate the significant sample test statistics from the non-significant one. So we have on this side, that side. Okay. If it's two-tail, then our alpha equal to 0.05. We need to divide by 2. That will make up a total of 5% and 2.5% in each size of the graph. Okay, so 0.025, 0.025, and that will give us these critical value. And if you use inverse norm again, you should arrive with the answer of Z is negative 1.96 on the left hand side, and then Z is positive 1.96 on the right hand side. Okay, so those are the critical values can be obtained using just the Z critical values from 5% significant level. For T critical values, we need the degree of freedom. So that's one method to determine where should we reject or not reject the sample test statistics. Another method is by finding the p-value of the sample test statistics. And the definition is confusing. To get the p-value is not so confusing, it's pretty easy. But to understand it, it does take some time to really process what exactly the p-value. Let's see here, how much left here? I think I'm gonna go ahead and pause on this note, and I'm gonna introduce p-value in the next video.